Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now we're just going to get started on our set of questions for today's session. Okay, so the first question asks the following. What mass of water at 25 degrees Celsius must be allowed to come to thermal equilibrium with a 1.85 kilogram cube of aluminum initially at 150 degrees Celsius to lower the temperature of the aluminum to 65 degrees Celsius? Assume any water turned to steam subsequently condenses. Okay, so first I'm just going to write down all the values that they give us. The mass of aluminum is 1.85 kilograms. But I will also convert this to grams just to get everything in the same units. So 1.85 kilograms is the same thing as 1,850 grams. Okay, so they also give us a T initial for the aluminum. I'm just going to do delta T of aluminum is equal to 150 degrees Celsius minus 65 degrees Celsius. And I'll also write down the delta T of the water. So delta T just means the temperature difference. So the delta T for water is 65 degrees Celsius minus 25 degrees Celsius. So what we also need in this question is something called the specific heat capacity. And we need this because the equation that we are going to use is Q is equal to mc delta T. So Q is heat, and the amount of heat that is given off and that is being used will be the same for both the aluminum and the water. Mass was given to us, which is the aluminum, and delta T is what I calculated already. So like I mentioned earlier, we just need C in order to answer this question, which is the specific heat capacity. So this varies depending on the compound that you have. So first I'm going to look up the specific heat capacity of water. So C water is equal to 4.184, and the units are actually joules divided by grams times degrees Celsius. So usually this is given in the question, but we also need to know the specific heat capacity of aluminum. So again, I'm going to do C aluminum is equal to 0.900 joules divided by grams times degrees Celsius. Okay, so now we have everything we need to answer the question. So step 1, is to first solve for Q needed to equilibrate the aluminum. So again, it was using Q equals mc delta T. We just need to plug those values in. So Q is equal to 1,850 grams. And first we'll be looking at aluminum, so I'm going to use the C value for aluminum, which is the 0.9 joules over grams times degrees Celsius. And then I'm going to multiply by the delta T for aluminum, which was 150 degrees Celsius minus 65 degrees Celsius. Okay, so now that we did that, we can say the Q is equal to 141,525 joules. Okay, so part 2 of this question is to then solve for the mass of water. Okay, so just rearranging the Q equals mc delta T equation, we're going to do mass is equal to Q divided by C times delta T. So we're going to plug in the Q value that we found in the previous step. This time we will divide it by the specific heat capacity of water, which is 4.184 joules over grams degrees Celsius times the delta T for water, which is 65 minus 25 degrees Celsius. And now you'll notice that our units should cancel out, and we are left with a value in grams, which is 845.6 grams. You can also convert this to kilograms, so 0.846 kilograms. Okay, so let's see what the junior tutor said. They have the given values for the different heat capacities of both water and aluminum. First, solve for the amount of heat needed to equilibrate aluminum temperature. And they got 141,525 joules. Then using this heat, compute for the amount of needed water. And they also got 846 grams. Okay, so I can say this solution is correct. Okay, so moving on to question 2, which asks, what is the chemical formula for nitrogen? So nitrogen in the atmosphere is a diatomic molecule. And what that means is that it's a molecule that contains 2 of the same atom. So in the case of nitrogen, the chemical formula is N2. So the junior tutor said, chemical formula of nitrogen is N2. Nitrogen gas naturally exists as a diatomic molecule, or a molecule that consists of 2 atoms of the same element. Yep, so this solution is correct. On to question 3. What is the molar mass of ammonia, which is NH3? So to answer this question, we need both the atomic masses of nitrogen and hydrogen. So these are values that you would just find on your periodic table. So I'm going to show we need the molar mass of nitrogen plus 3 times the molar mass of hydrogen, since there are 3 atoms of hydrogen in the ammonia molecule. So the molar mass of nitrogen is 14.01 grams per mole, and the molar mass of hydrogen is 1.01 grams per mole. Okay, so if we add all these values up, we end up with a value of 17.04 grams per mole. Okay, so the junior tutor said, in definition, the molar mass is the mass of a given chemical element or chemical compound in grams divided by the amount of substance in moles. The molar mass of a compound can be computed using a periodic table by adding the standard atomic masses of the individual elements or atoms. It is used to compute for the number of moles of a certain compound to give its mass. To compute for the molar mass of ammonia, we need to first get the individual atomic masses of each element. Remember that for every 1 mole of NH3, there are 1 mole of nitrogens and 3 moles of hydrogen. Therefore, we need to multiply the atomic masses of nitrogen and hydrogen to 1 and 3 respectively. So they just summarize the atomic masses of both nitrogen and hydrogen. And then solving for the molar mass of ammonia, we have 14.01 plus 3.024, and they got a value of around 17.034 grams per mole. Yep, so this solution is correct. Okay, so moving on to question 4. What is the molar mass of sodium chloride, which is also known as table salt? Okay, so to answer this question, we would need the molar masses of both sodium and chloride. And since there is 1 atom of each, we don't need to multiply these values by any whole numbers. We would simply just need to add up their 2 atomic masses, which you can just find on the periodic table. So the atomic mass of sodium is 22.99 grams per mole, and the atomic mass of chlorine is 35.45 grams per mole. Okay, so adding these 2 values up, you end up getting 58.44 grams per mole. Okay, so the junior tutor said to solve for the molar mass of sodium chloride, first determine the molar mass of each element. Sodium 22.989 grams per mole, chlorine 32, I think they meant to say 35.45 grams per mole. Next, since all elements of the compound contain no subscript, it means it consists of 1 atom of each. Add the molar mass of each element. So again, this should read 35.45 grams per mole, and they should have gotten 58.44. So I'm just going to make that correction. Okay, so I just explained that since the molar mass of chlorine is 35.45, the molar mass of sodium chloride will add up to 58.44. So on to question number 5. What is electronegativity? Okay, so electronegativity is the tendency of an atom to attract electrons. So, for example, since noble gases are inert, their electronegativity values are equal to 0. And another example would be the chlorine atom. It has a total of 7 valence electrons, and it really wants to gain a full octet. So therefore, the chlorine atom really wants to attract another electron. So therefore, chlorine has a high electronegativity value. Then I'll just draw out that it wants to gain another electron and become Cl- in order to get that full octet. Okay, so let's see what the junior tutor said. Electronegativity is a property of an element or atom, which is described as its tendency to attract a pair of shared electrons towards itself in a molecule. The most electronegative element is fluorine, with a value of 4 according to Pauling's scale, while the least electronegative elements are francium and cesium, with a value of 0.7. I wouldn't say they are the least electronegative, since technically noble gases would be more, but the answer's still correct. I'll probably just add a little note. But I'll still say this solution is correct because they gave the correct definition of electronegativity. Okay, so on to question 6. How many cups are in 100 milliliters? So the conversion factor for cups to milliliters are for every 1 cup, this is 236.6 milliliters. So now let's solve for how many cups are in 100 mils. So first I'm just going to write my unknown, x cups over 100 mils is equal to my conversion factor. In the same order, 1 cup divided by 236.6 mils. So now I'm just going to solve for x. I'll multiply both sides by 100 mils. And then our units of milliliters will cancel out. And we are left with the value in cups, which is 0.423. Okay, so there are 0.423 cups in 100 mils. So the junior tutor said there are 236.588237 milliliters in 1 US cup. Therefore, there are 0.422 cups in 100 mils according to the US measurement. Yep, so the solution is correct. Moving on to question number 7. Is xenon tetrafluoride a polar or nonpolar bond? So first, to answer this question, we would need the electronegativity values of both xenon and fluoride. So I'm going to look these values up. So let me just search electronegativity, negativity values, and then the periodic table. Okay, so the electronegativity of first xenon is found right at the end here, and it is 2.6. And the electronegativity value for fluorine is up here, so it is 4.0. So now we want to take the difference in electronegativity values. So it's going to be 4 minus 2.6, which is equal to 1.4. So therefore, this is a polar bond. But I also wanted to just show what would happen if we would draw out the molecule of xenon tetrafluoride. There are 4 fluorine atoms symmetrically like this, and there's also 2 lone pairs. So as you can see, this is a symmetrical molecule, and also all these polar bonds can be written like this to show all the dipole moments, since fluorine is more electronegative than xenon. However, you'll notice that these bonds tend to cancel each other out. So the xenon tetrafluoride molecule as a whole is actually nonpolar. Even though the bonds that are within the molecule all of them are polar, the molecule itself is nonpolar. So I'll just write the explanation. So since it is symmetrical, and also the dipole moments are cancelled out. Okay, but to answer the question, the xenon and fluorine bond is polar. So the junior tutor said, xenon tetrafluoride is a bond between an atom of sulfur, 2 atoms of chlorine. I think they meant between an atom of xenon and 4 atoms of fluorine. To determine if it is a polar or nonpolar, we have to solve for the difference in their electronegativity. Difference greater than 0.4 means that the bond is polar. Xenon has an electronegativity of 2.6, while fluorine has an electronegativity of 3.98. Okay, so they found the difference in electronegativity, and since it is greater than 0.4, that means the bond is polar. Let me just fix the typos. So this solution is correct. Let me just make some corrections. So this should be greater than 0.4. Therefore, polar bond. Yep, but I'll still say this solution is correct. Moving on to question number 8. What is a reduction reaction? So a reduction reaction is a half reaction that involves an atom gaining an electron. Also, you'll also notice that its oxidation number decreases. Okay, so let's see what the junior tutor said. Oxidation reduction reaction, also called redox reaction, is any chemical reaction in which the oxidation number of a participating chemical species changes. Many oxidation reduction reactions are as common and familiar as fire, the rusting and dissolution of metals, the browning of fruit, and the respiration and photosynthesis. 2 species that exchange electrons in a redox reaction are given special names. The ion or molecule that accepts electrons is called the oxidizing agent. By accepting electrons, it causes the oxidation of another species. On the other hand, reducing agent is the ion or molecule that donates electrons. Redox reactions can be easily memorized using the mnemonics below. So they have G-E-R-O-A. So gain of electrons is reduction, oxidizing agent. And LEO-RA, lose of electrons, oxidation, reduction agent. So I'm just going to write over here, also use a term called oil rig. So that means oxidation is losing electrons and reduction is gaining. You can also use Leo-Ger, which is similar to what the junior tutor said. Losing electrons is oxidation, and gaining electrons is reduction. Okay, so to continue on, the reduction reaction is a part of redox reactions in which the number of electrons associated with an atom or a group of atoms is increased. Yep, so that means it's gaining electrons. The electrons taken up by the substance reduced are supplied by another substance, which is thereby oxidized. Consider the reaction between magnesium metal and oxygen to form magnesium oxide. 2 magnesium solid plus oxygen gas makes 2 moles of magnesium oxide. First, the oxidation state must be assigned in each element on both sides of the equation. The oxidation state of an element corresponds to the number of electrons that an atom loses, gains, or appears to use when joining with other atoms and compounds. Following are some rules for assigning oxidation states. Oxidation state of an individual atom is 0. So if you look at the example, both magnesium and oxygen have oxidation numbers of 0. Total oxidation state of all atoms in a neutral species is 0, and in an ion is equal to the ion charge. Group 1 metals have an oxidation state of +1. Group 2 metals have an oxidation state of +2. Oxidation state of fluorine is -1. Hydrogen generally has an oxidation state of +1. So the exception is when it is paired with a nonmetal, like sodium hydride, it would have a -1 oxidation state. Oxygen generally has an oxidation state of -2 in compounds. So the exception is when oxygen is in peroxide. It has a -1 oxidation state. In binary metal compounds, group 17 elements have an oxidation state of -1, group 16 -2, group 15 -3. So this is their example. The magnesium increases from a 0 to +2 oxidation state, while the oxidation state of oxygen decreases from 0 to -2. This reaction, the oxygen gained electrons, thus it was reduced. Oxygen also served as the oxidizing agent. Yep, so that was great. So this solution is correct. Okay, so on to question 9. What is O2 and O3? Okay, so let's first talk about O2. So it is 2 oxygens double bonded together, and I also showed the lone pairs on the oxygen atoms. And O2 is what is found in our atmosphere. We also need it to breathe, so it is very much needed for human and animal life on Earth. O3, on the other hand, is also known as ozone. So its structure is shown here. Its structure has 3 oxygens. So one is negatively charged. This one will be positively charged. So this is an ozone molecule, and it is less stable than just O2 gas. Okay, so the junior tutor said oxygen gas is the natural form of the oxygen element. Means that in a standard setting, the oxygen will be in the form of gas. It is the air that is needed by animals to breathe, and it comprises about 21% of the Earth's atmosphere. Under certain circumstances, oxygen can be in the form of O3, wherein 3 oxygen atoms are covalently bonded to each other. This form of oxygen is highly unstable and only exists in specific conditions. Ozone is the one protecting the living creatures on the Earth from ultraviolet rays. Yep, so this solution is correct. Okay, so moving on to question number 10. In PV equals nRT, what is R? That is a great question. So let me just define all the different terms in PV equals nRT. So the P stands for pressure. The V is volume. N is number of moles. R is what we call the gas constant. And T is temperature. So in green, I'm going to write down all the values that are in standard atmospheres, or I guess in an ideal situations. So ideally, pressure is 1 atm. Volume will be equal to something we call molar volume, which is 22.4 liters. And I will solve for the gas constant, but I'll just write down its units, which is liters times atm over mole times Kelvin. And for temperature, I will input 273.15 Kelvin, which is the 0 point on a Kelvin scale. And lastly, for number of moles, it will just be 1 mole. Okay, so now we're going to solve for R, which is our gas constant. So just rearranging the equation, R equals PV over NT, where pressure is 1 atm, the volume will be 22.4 liters, number of moles will be 1, and the temperature is the 0 point on the Kelvin scale. Okay, so solving for R, we end up getting the ideal gas constant, which is equal to 0.08205 liters times atm over mole times Kelvin. Okay, let's see what the junior tutor said. The equation PV equals nRT is the ideal gas equation. This equation relates the pressure, volume, temperature, number of particles in a gas. R here is the universal gas constant. Value of R used in the equation depends on the units of the other quantities. So this is true as well. So like it can be equal to 0.08, which is what we calculated. Also, depending on what units you have, it can also be equal to 8.314. So R is equal to PV equals over NT when the pressure, volume, and temperature are expressed in, I think they mean ATM and liters. Well, meters cubed is the same. R is equal to 0.08 when the pressure, volume, and temperature are expressed in ATM, liters, and Kelvin. So the last part makes a little more sense, so I'm just going to say this solution is correct. Okay, so now we are moving on to question 11. What is the octet rule? So the octet rule is the tendency of atoms to prefer 8 electrons in their valence shell. So let's say we had chlorine, for example, has the 7 valence electrons, and it really wants to gain another electron to be more stable. So this is an example of the octet rule. So let's say it gained an electron. So now chlorine becomes the chlorine ion because it has an extra electron. And we typically find the chlorine ion more commonly since it is in its more stable form. Okay, so the junior tutor said the octet rule is a rule of thumb observed in main group elements wherein when an atom achieves a complement of 8 valence electrons, then it will form covalent bonds. Recall that valence electrons are electrons in the outer shell of a particular atom. Yep, so the solution is correct. Okay, so on to question 12. What is the molar mass of sodium hydroxide? Okay, so sodium hydroxide, if we don't know the chemical formula, it is composed of a sodium ion, which is Na+, and a hydroxide ion, which is OH-. So we end up getting NaOH for our chemical formula. So to calculate for the molar mass of NaOH, we would need all the molar masses of the atoms involved. So this is equal to the molar mass of sodium plus the molar mass of oxygen plus the molar mass of hydrogen. And since there are only one atom, there's only one atom of each of these elements, I don't need to multiply by anything. So let's just plug in our molar mass values. So these are the values that you would just find on your periodic table. For sodium, it is 22.99 grams per mole. For oxygen, it is around 15.99 grams per mole. And the molar mass of hydrogen is 1.01 grams per mole. So adding all these values up, we end up getting around 40 grams per mole for the molar mass of sodium hydroxide. So the junior tutor said the molar mass of sodium hydroxide is 40 grams per mole. Step 1. Determine the molar mass of elements present using the periodic table. Sodium 22.99, oxygen 16, hydrogen 1.01. Step 2. Since there is only one atom per element present in the molecule, we add up all the molar masses. Molar mass of sodium hydroxide is equal to 22.99 plus 16 plus 1.01, which is equal to 40 grams per mole. Yep, so I'll verify that this solution is correct. Okay, so moving on to question 13. The density of sulfuric acid is 1.84 grams per milliliter. What volume of this acid will weigh 171 grams? Okay, so let's first write down what we know. This is the symbol for density, which is also called rho, I believe. So the density is equal to 1.84 grams per milliliter. We are looking for volume, which will be a value in milliliters. And they also give us the mass of the acid, which is 171 grams. So first, let's recall that the density is equal to mass over volume. So now that we know this equation, we can rearrange it to solve for volume. So volume is equal to mass over density. So this is equal to 171 grams divided by 1.84 grams per milliliter. And we know that we did the math right if our units for grams should cancel out and our units for milliliters should be our unit. Okay, so doing this division, you end up getting 92.93 milliliters of sulfuric acid will weigh 171 grams. Okay, so the junior tutor said, density is the measure of the mass of a substance per volume. Mathematically, it is expressed as density equals mass over volume. Rho is equal density, m equals mass of the substance, v is the volume displaced. Rearranging the formula to solve for v is equal to mass over density. Substituting the given to solve for the volume of sulfuric acid, we have 171 grams divided by 1.84 grams per milliliter. It's equal to 92.93 mils. Therefore, the volume of sulfuric acid is 92.93. Yep, so this solution is correct. Okay, so moving on to question 14. How do we convert ppm to molarity? So ppm is also known as parts per million. Okay, so since we know ppm is in parts per million, that is similar to it having a concentration of milligrams per liter. So if ppm is in milligrams per liter, Then we also need to understand that molarity we want in moles per liter. So to answer this question, we would also need to convert milligrams to moles somehow. So therefore we need the molar mass of like your solute to answer the question as well. So it's not just like a simple conversion. We're also going to need the molar mass of that substance. So let's say we started off with 1 milligram per liter. First, let's convert it to grams. So to do this, we will multiply by the conversion factor of grams to milligrams. So there are 1,000 milligrams in 1 gram. Okay, so this will cancel out our milligrams. And we also need to convert our grams to moles. So I'm going to multiply this again by the reciprocal of molar mass. So the reason why it's 1 over molar mass is because the units for molar mass is grams per mole. So if we put this in the denominator, we can cancel out our grams and bring our moles up as the numerator. And then that is how we get our units to be moles per liter. Okay, so let's see what the junior tutor said. Definition of ppm, parts per million, is 1 milligram of solute per 1 kilogram of solution. For an aqueous solution where the solvent is water, this can also be expressed as 1 milligram of solute divided by 1 liter of water. Molarity, on the other hand, is the number of moles of solute to the number of liters of solution. Hence, to convert ppm to molarity, we must know the molar mass of the solute so we can get the number of moles from the given mass using the equation N equals m over m. So, yeah, so that's correct. I'm also just going to write down what I wrote as well. Okay, so I'm just going to show. Okay, so this solution is still correct. Question 15 just asks, what is the molar mass of sulfur dioxide? So to find the molar mass of sulfur dioxide, we would need the atomic masses of both sulfur and oxygen. So these values are just found on your periodic table. So molar mass of sulfur plus 2 times the molar mass of oxygen, since there are 2 atoms of oxygen in sulfur dioxide. So the molar mass of sulfur is 32.07 grams per mole, and the molar mass of oxygen is 15.99 grams per mole. Adding these values up, we end up getting 64.07 grams per mole for the molar mass of sulfur dioxide. So Junior Tutor said, in definition, the molar mass is the mass of a given chemical element or chemical compound in grams divided by the amount of substance in moles. Molar mass of a compound can be computed using a periodic table by adding the standard atomic masses of the individual atoms or elements. It is used to compute for the number of moles of a certain compound to give its mass. To compute for the molar mass of sulfur dioxide, we need to get first the individual atomic masses of each element. Remember that for every 1 mole of SO2, there's 1 mole of sulfur, 2 moles of oxygen. Therefore, we need to multiply the atomic masses of sulfur and oxygen to 1 and 2 respectively. Atomic mass of sulfur is 32, atomic mass of oxygen 16. Solving for the molar mass of sulfur dioxide, they get 64.065 grams per mole. So this solution is correct. Okay, so I think we have time for one more question. Number 16 asks, how do you calculate the mass of zinc that is consumed when it is made to react with iodine to produce zinc iodide? So this is the chemical equation. Zinc plus iodide makes zinc iodide. So we would just pretty much need all the masses we need the mass of iodide to calculate for the moles of iodide. To find the moles of zinc. So since they react in a 1-to-1 ratio, they will have the same number of moles. And then once we have the moles of zinc, then we can find the mass of zinc. Using number of moles times molar mass. Okay, so let me just write here that the number of moles of iodide can be found when you have the mass divided by the molar mass of iodide. Okay, so let's see what the junior tutor said. To determine the mass of zinc that is consumed in the reaction, the number of moles of iodine must be calculated from the given mass by dividing it by its molar mass. Then it must be multiplied to the mole ratio between zinc and iodine to determine the number of moles of zinc. Lastly, the number of moles of zinc must be multiplied to the molar mass to calculate its mass. So here they have an example, which is good. How many grams of zinc must be consumed to react with 15 grams of iodine to produce zinc iodide? So they start off with the mass of iodide, and then they divide it by the molar mass of iodine, 253.8. And since they have a 1-to-1 mole ratio, they'll have the same number of moles. And then we'd simply just need to multiply the moles by the molar mass of zinc, which is 65.38 grams, to get 3.86 grams of zinc that is consumed in the reaction. Yep, so this solution is correct. Okay, so that is all the time we have for this session. And if you like today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description below. Also, don't forget to leave a like and a comment if you enjoyed today's video. Don't forget to share it with all your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.